Two breakthroughs just landed that rewrite what we think open source and small footprint AI can do. One shows a model that knows when to think out loud and when to get straight to the point. The other turns giant, messy industrial systems into something a language model can predict with startling precision. If you've been waiting for a sign that the AI landscape is shifting again, this is it. First up, Hermes 4. It arrives in 3 sizes, topping out with a colossal model built on the latest open foundations. And the headline is simple. It reasons. Not just more, but smarter. Ask it something straightforward and it answers cleanly. Throw it a naughty problem and it flips into a deliberate mode, writes out a full internal line of logic inside special tags, and guides you step by step to the answer. The result is a model that doesn't drown you in explanations when you don't need them, but shows it's working when you do. What makes that possible isn't a secret data stash. It's post-training craft. The team built a synthetic data engine called DataForge that doesn't scrape the internet and hope for the best. Instead, it takes structured inputs and runs them through a directed graph of transformations. Imagine feeding in a factual article and watching it become a song, then turning that song back into instructions and answers. Each node has requirements, an output spec, and explicit rules for reshaping content. Chain those nodes together and you get a vast curriculum spanning styles, domains, and reasoning traces. The scale matters, but so does the shape. Hermes 4 was fed millions of examples spanning billions of tokens, with long reasoning sequences that are multiple times larger than typical training traces. Some examples stretch to tens of thousands of tokens. That teaches the model to hold a complex thought for the long haul without dropping the thread. Of course, synthetic generation is the easy part. The hard part is ruthless filtering. That's where an open reinforcement learning environment called Atropos comes in. Think of it as a guardian that runs a battery of checks before any example is allowed to teach the model. Formatting has to match dozens of templates. Instruction following gets stress tested. Outputs must validate against schemas. Tool use is simulated so the model learns agent-like patterns, not just pretty text. Crucially, when more than one path leads to a correct answer, the pipeline keeps those alternatives. That diversity is what trains flexible reasoning rather than rote memorization of a single route. If you've tested reasoning models, you know the next problem: runaway rambling. Once a model starts thinking, it can forget to stop. The smallest Hermes variant was hitting context limits a majority of the time when deep thought kicked in on certain benchmarks. The fix was elegant. They ran a second fine-tuning stage dedicated purely to stopping. Generate extra long traces, truncate them, add closing tags, and only update the tokens that teach the model how to wrap up gracefully. By separating how to think from how to stop, they cut runaway generations dramatically across math and coding benchmarks while keeping accuracy in the same ballpark. It's the difference between a model that impresses in demos and one you can actually use day to day. The numbers back it up. On tough reasoning sets in maths, science, and coding, the largest Hermes 4 posts state-of-the-art scores for an open model. It even stands out on refusal and moderation tests, engaging with sensitive prompts in a measured, neutral way instead of reflexively shutting down. That alignment stance is deliberate. Address the question, stay safe, stay calm. Under the hood, the engineering is as serious as the modeling. Training ran across a large cluster of cutting-edge GPUs with careful orchestration. Long sequences were packed efficiently. So compute wasn't wasted on filler tokens. Learning rates were tuned over thousands of steps. Multiple kinds of parallelism were layered so every chip stayed busy. When you see the results, you're not just looking at a clever data set. You're seeing what happens when open research and top-tier systems work hand in hand. Why does this matter? Because it shows open source can compete in reasoning without closed data or secret sauce. Transparent, customizable, and fast-moving. If you care about building, auditing, or extending these systems, that's a big deal. Now pivot to Google, because their announcement hits a totally different pain point, predicting how enormous, ever-changing systems will behave. Data centers, manufacturing lines, massive IoT networks. The traditional approach is to crush logs and configurations into flat tables, craft features by hand, and hope the regression model holds together when the hardware or workload changes. It's slow, brittle, and expensive. Google's answer is a new family of models called Regression Language Models. Instead of distilling the world into a spreadsheet, they serialize system state as structured text, often JSON or YAML. Inputs are text. Outputs are predictions as text. A workload description goes in. An efficiency estimate comes out. No bespoke feature engineering. No weeks of rework every time a cluster evolves. If you can describe it, you can model it. The architecture is intentionally simple. A compact encoder-decoder trained directly on input-output pairs for the target task, with a number-aware tokenization that treats sign, mantissa, and exponent consistently, so floating point values aren't awkward strangers in the vocabulary. Because the model isn't burdened with broad pre-training, it fine-tunes. Quickly, hundreds of examples can be enough to adapt to a new cluster or a new metric. It also eats long inputs, so thousands of tokens of logs and configs can be fed in raw. Performance is the eyebrow raiser. On internal data center workloads, these models hit extremely high-rank correlations for throughput and efficiency, and slash mean squared error by orders of magnitude compared to traditional baselines. And they don't just spit out a single number. By sampling multiple outputs, they quantify uncertainty, capturing both natural noise and blind spots from missing signals. That unlocks practical workflows, Bayesian optimization for tuning, digital twins for what-if scenarios, and closed-loop controllers that can weigh risk, not just point estimates. The bigger insight is philosophical. For years we bent complex systems to fit our models. Now we can bend the models to fit the systems. Describe the world faithfully, let the language model. Learn the mapping, and update it in hours when reality changes. Cloud scheduling, factory throughput, power grids, lab experiments with shifting protocols, anywhere feature engineering. Slows you down, text-native regression offers a faster, more adaptable path. Put the two stories together and you can feel the ground moving. On one side, open models are mastering structured, selective reasoning with the transparency builders crave. On the other, lean text-to-text forecasters are making prediction and control feel like natural language problems. Both trends reduce friction, both put more power in the hands of practitioners, and both suggest we're heading into an era where the best systems aren't just bigger, they're better shaped to the tasks we actually have. So here's the takeaway. We've crossed a threshold. Open source can think deeply and stop cleanly. Small models can read the pulse of giant machines and tell you what happens next, with confidence attached. If you're building with AI, this is your cue to experiment. Wire up a reasoning mode you can trust. Describe your real-world system as text and ask for tomorrow's answer today. The tools are ready. If this gave you a clearer view of what's coming, share it with someone who needs to hear it. Make sure you're subscribed so you don't miss the next leap. And as always, thanks for watching.